Hello, this is the first in a sequence of video lectures covering recent advances in robust statistics, particularly in high dimensions. Before I actually dive into the material though, let me get some administrative stuff out of the way. So these lectures are based off of some material I taught at the course at the University of Washington last fall. Lecture notes for that course are available online, and I'll post a link to them in the description below. Secondly, I will be assuming some prerequisites throughout these lectures. Particularly, I'll be assuming some degree of mathematical maturity, specifically comfort in probability theory. So you should be familiar with things like Markov's, Chebyshev's, Chernoff, Hufting, that kind of stuff. Additionally, I would say that some grounding in machine learning or statistics would be useful, although not strictly necessary. Okay, with that out of the way, let me just dive in. So what is robust statistics? Well, at a very high level, qualitatively, I would say that robust statistics is a study of what we can learn when we're given a data set that has been polluted by a small fraction of potentially adversarial outliers. This is something that happens in practice all the time for any number of reasons that we may or may not understand. So for instance, this can happen because of statistical phenomena like model misspecification. So imagining I'm modeling this really complicated real-world thing that I don't fully understand. So I'm going to take this statistical model, which slightly oversimplifies things. But in the process of doing so, it's going to miss some things like second-order effects, some smaller order things. And these, things that I'm missing end up as being systematic noise, which in the worst case might as well be adversarial, since we don't know how to control them. So pictorially, what I'm imagining is the following. I'm modeling some behavior with some relatively nice distribution, but of course, reality is often disappointing. And instead, I have some, the true distribution looks like this, and these sorts of spikes, which can happen anywhere, in the worst case could look like adversarial outliers. Certainly we have no control over where they happen. Another more direct source of such outliers is just from tampering. So imagine I'm given a data set that has been tampered with by some adversary. So for instance, a setting which just comes up all the time is crowdsourcing. So in many modern machine learning applications, I have to crowdsource the collection of my data because I need a really large data set. But in the process of doing so, I can't fully vet all the users who are providing me information, and it's very possible, and often happens, that a small set of these users are going to feed me bad data to try to change the behavior of my algorithm. So the goal here is to prevent that from happening. So the question is, when can we design algorithms that can handle this type of noise? And let me formalize this notion a little bit more. So in these lectures, we will typically consider a very strong notion of adversarial outlier. Particularly, we will consider adversaries which can change an epsilon fraction of the data in any way they so desire. So pictorially, here's what's going on. Here I've drawn n IID points from a nice distribution D. Okay. And then what I have to do is I have to give this set of points. I don't actually get to see the set of points. I give it to an adversary. Okay, and this adversary is very powerful and very malicious. And they don't like us. And they know, again, everything. They know the data. They know our algorithm, potentially, that we're going to be using. And they know the problem that we're trying to solve. And what they're going to do is they're going to be like, I don't like this point. I'm going to move that point from here to here. I don't like this point. I'm going to move it here to here. I don't like this point. I'm going to move it here to here, and so on and so forth. The only constraint being that they can only touch an epsilon fraction of these points. And then afterwards, this new set of points is given to us, of course without the colors. And our goal is to recover information about the original distribution that generated the original uncorrupted points. Okay, so formally, we can think of this changing process as a two-step process, whereby the adversary first removes an epsilon fraction of the good points, then adds back in an epsilon fraction of any points that they want. So formally, definition, we say that a set of points S is epsilon corrupted from a distribution D if it can be written as the following. S is equal to good set minus remove union bad, where good is a set of n IID samples from my distribution D, so this was the original set of points before tampering. Removed is a subset of the good points, and the only constraint other than that on the removed and bad points is that the number of points that I removed is equal to the number of bad points I added, and is at most an epsilon fraction of the overall number of points. So n is the size of the size of the original good set. Okay? And it is not too hard to see that without loss of generality, we might as well take this less than or equal to be equal to, because in the worst case, the adversary could just simply choose to not do anything to solve some set of the points, and this is just an equivalent. Okay, this formulation is what we're going to be working with a lot in this class, so it's important that you understand this. And a couple of notational shortcuts. This is the thing I just wrote is a little bit clunky, so typically we'll abbreviate this slightly as S is equal to S sub G union S sub B sub minus S sub R. So S sub G stands for good, S sub B is bad, S sub R is removed. In the lecture notes, you'll often see this written out as S sub good union S sub bad sub minus S sub R, but this is just a little bit clunky for in-person lectures, so I'm going to abbreviate this. And one final thing is that if S is an epsilon corrupted set of points from D, we'll often denote this as S is drawn epsilon corrupted from D. So this is how we will notate that. Okay, so now the goal is we are given a set of points which is epsilon corrupted, which has this epsilon fraction of potentially adversarial outliers. And now we want to solve some problem. So we want to do some statistical task. And in this area, I claim that there are at least 3 important criteria. There are, of course, others as well that one should concern themselves with. So these 3 are the following. First, asymptotic error. And this is asking, if I take epsilon, the fraction of bad points, to be fixed, and I let n go to infinity, how much error does my estimator achieve? This is the asymptotic error. Second, equally important question is statistical rate, which is how fast do I approach this asymptotic error as I increase the size of my data set. Okay, and finally, a slightly orthogonal concern, but I would also say equally important, is runtime, which is simply how fast can I compute my estimator. Right, and this is a little bit different, but again, just as important, because no matter what nice statistical properties I have for my estimator, if I can't compute it, it's not going to be very useful for me in practice. Okay, so now we have this definition of epsilon corruption. We'll actually see a couple more definitions in the next lecture, and we'll see how they're related. Qualitatively, there's not huge differences, it turns out, at least in the results that we can get, typically. But for now, our algorithms will work in this in this strong notion of corruption, so we might as well. Okay. So now we want to solve some statistical problems. But before I consider robust versions of these statistical problems, let me step back a little bit and consider just regular, non-robust versions of these problems. The following is an extremely oversimplified view of traditional statistics or machine learning. And it can be thought of as the following. What statistics and machine learning is trying to do is you're given n independent draws from some distribution D, so x1 through xn. And typically I'll think of my distributions as being supported over RD. So pictorially here I've drawn them as points in R2. And then my goal is to learn some information about the underlying distribution. So some basic things I could try to learn are, for instance, the mean, or I could try to learn the variance, or in high dimensions, the covariance. Of course, oftentimes in statistics and machine learning, our goal is to learn much more complicated things. Like, for instance, our distribution is not over RD, it's over labeled tuples, and the goal is to, given a fresh sample, predict its label. Okay? But it turns out in the robust setting, even these very basic things, like mean and variance, become not so easy to do, and understanding how to do them becomes like an important building block for getting to these much more complicated things, which we will get to eventually in this course. So for now, let's focus on how to do mean estimation. Before we do robust mean estimation, let's just do regular, not robust, mean estimation. So how would I do it? Well, first of all, even in this nice non-robust setting, I still need some assumptions on my distribution to say anything meaningful, right? If my distribution is completely arbitrary, then first of all, it might not even have a finite mean. And second of all, there's no way I'll ever get any finite sample guarantees from my mean. So typically we make some assumptions about our distribution. So one of the nicest ones, at least in terms of mean estimation, is like D is Gaussian. Just because now we have a lot of concentration, everything is nicely behaved. But of course this is relatively strong, even if it is a standard assumption. So oftentimes, our data might not behave this way. So we might consider relaxed notions, like for instance, it just has bounded moments. So for instance, maybe it has variance 1. Okay, so now let's consider the one-dimensional case of this problem. So here, D is a Gaussian, just means that it's some Gaussian with mean mu and variance 1. D has bounded moments. Let's just consider the setting where D has variance 1. And I should say that throughout this lecture, I'm always going to assume that my distributions have variance 1, but it's really easy to see that the algorithms I'm going to consider are very scale invariant, and so the results scale in a natural way. For instance, if my Gaussian has variance sigma squared. Okay, so in these settings, what would I do? Well, there is at least one naive estimator, I claim, and that is just the empirical mean of my data. So I just take the average of my data points. So mu hat is just the sum, or the average, I should say, of the xi. And in this simple univariate setting, this works great. Right, so here it's not super important to parse the exact details. But if I have samples from a Gaussian, and I take the empirical mean, then essentially I get the following error, that the expected difference between the empirical mean and the true mean scales like square root of 1 over n. And I should say, throughout these lectures, I will use this less than squiggly notation to denote that it is true up to constant factors that I will ignore. Okay, but this says that up to constants, the error in expectation is square root of 1 over n. And similarly, if I care about probability, high probability bounds, then with probability 1 minus delta, I get essentially the same thing times square root log 1 over delta, which is a fairly minimal overhead. Now, if my samples are from a distribution with bounded variance, and that's my only assumption I'm making, then I can't get quite as good bounds overall. So actually my expected error is the same. Up to some universal constant, it is also square root of 1 over n, but the high probability bound is a little bit worse. It's square root of 1 over n times square root of 1 over delta. Okay, so this is somewhat worse. But it's still pretty good. In particular, notice that as n goes to infinity, all these bounds are vanishing. And at the very least, for both of these settings, the expected error guarantee is minimax optimal. But now let's turn our attention to the question when there are outliers. So now let's consider the robust setting. And there's a very, the first pass is maybe the empirical mean still works. But the answer to this is a fairly resounding no, it does not. It fails miserably. And to see this is very simple. I'm just going to draw this in 2 dimensions. But what the adversary can do is simply remove a point, change one point from some anywhere, it doesn't really matter, and move it arbitrarily far away at infinity. And you can see it has unbounded influence on the empirical mean, and so the empirical mean will have arbitrarily bad error. So in this robust setting, the empirical mean is extremely non-robust. However, there are 2 estimators that do work, and they're not too hard, at least in this simple univariate setting. And we will cover them in this class, and we'll try to prove the bounds for them. Okay, so these 2 estimators that I claim will work are first of all the median, and then the second is a truncated mean. So both of these estimators are fairly intuitive. Perhaps you've taken a statistics class and you've seen or you've heard that a median is a good robust version of a mean that is resilient to outliers, and we'll see exactly why in a second. And also truncated mean is very obvious. It's just trying to exactly rectify this problem that I had, because this point out at infinity certainly looks like an outlier, so I should just be able to remove it, and then maybe the mean of the remaining points is not so bad. Okay. However, there's already some interesting details here. It's actually going to be important in what settings we decide to analyze these 2 estimators. And we'll get to a comparison between these things at the end of the lecture. This will actually bring us some bigger questions about sort of the philosophy behind robust statistics, as we'll see. So in particular, what I'm going to do is I'm going to analyze the median in the setting where I assume my inliers are Gaussian. And here, for the truncated mean, I will analyze it in the setting where my distribution has bounded variance. And this is not entirely arbitrary, as we will discuss later on. Okay, so let's just get into it. So let's consider the median in the setting where there are Gaussian inliers. Okay, so formally, for a set of endpoints, let let median of t, or just denote the median of t using the shorthand. Okay. And the goal again is this setting where we have an epsilon corrupted set of points from Gaussian with mean mu and variance 1, and the goal is to learn mu. So before I actually state the guarantee, let me recall some basic stuff. So let me let phi be the CDF of the standard Gaussian. So this is something like the error function. It's simply phi of t is the probability that a standard Gaussian is less than t, and you can write it with this formula here. And it looks like this sigmoid looking thing, which is 1/2 at 0 and asymptotes at 1. Okay? So the theorem I'm going to prove, it looks a little bit complicated, but I'll parse it for you, which is the following. Suppose S is an epsilon corrupted set of points from a Gaussian with mean mu and variance 1. So to recall, this means that S can be written as a good set minus removed union bad. Okay, and suppose it has size n, and let the epsilon corruption, let the epsilon there be less than 1/2. Let t be such that t is greater than this phi inverse of 1/2 plus epsilon. Then we have this slightly complicated looking guarantee. The probability that the median of S minus mu exceeds t is at most 2 times the exponential of 2n times this quantity, which you can read. But let me parse this in a way that makes a little bit more sense. So first of all, this guarantee on t, or this condition on t, is not so, it's fairly natural. In particular, it makes sense for any epsilon which is less than 1/2. This is because phi inverse of 1/2 plus epsilon, so 1/2 plus epsilon, if epsilon is less than 1/2, will be less than 1, and phi inverse of that will at least be finite. So at least this guarantee will make sense for some t's. However, notice that when epsilon is 1/2 or greater, then phi inverse of 1 is infinite, just because if you look at this, it asymptotes at 1. So that means that this theorem makes sense for any epsilon less than 1/2. And when you think about it, this makes a lot of sense. Because if epsilon is equal to 1/2, that means half the points are inliers and half the points are outliers. And at least in this vanilla setting, there's no way to distinguish which points are the outliers and which points are the inliers. The adversary could just have planted another equally valid Gaussian somewhere else, and you can't distinguish between the inliers and the outliers. We'll actually get to this setting later. It turns out you can at least say something a little bit more interesting, but you need to relax the problem a little bit. Okay, but at least for this setting, we can say that epsilon is equal to 1/2 is something called the breakdown point, meaning that the median makes sense or gives you good guarantees as long as the total number of outliers is strictly less than 1/2. Okay, so it breaks down at 1/2 essentially. Oop. Excuse me, that's my cat. Second remark, this expression on the right hand side here looks a little bit complicated, but really is not so bad, especially in the regime where epsilon is relatively small. So when epsilon is close to 0, Taylor approximation of phi, so you can see pictorially, phi is quite smooth around 0, and phi inverse will therefore be quite smooth around 1/2. And so you can do a Taylor approximation, and you can just you can just estimate that phi inverse of 1/2 plus epsilon is essentially linear. It's this constant, root 2 pi times epsilon plus order epsilon squared deviations. So that means when epsilon is relatively small, this guarantee here is roughly saying that t needs to be order epsilon, or theta of epsilon. And then if we plug that guarantee back in here, if we set t is equal to theta of epsilon here, then we can just also plug in the Taylor approximation for the standard for just phi, and then phi of t is roughly speaking just 1/2 plus t over root 2 pi. And recall that t itself was roughly root 2 pi times epsilon. So then this expression simplifies a lot, and essentially what I'm getting at is the following corollary follows, which is that if epsilon is sufficiently small, then the probability that the median of S minus mu exceeds something times epsilon, this constant, 2 times root 2 pi epsilon, it decays exponentially, like minus omega of n times epsilon squared. So in particular, if I set n to be omega of log 1 over delta over epsilon squared for any delta, then we just simply get the probability that the median of S minus mu exceeds 2 root 2 epsilon is less than or equal to log, or excuse me, less than or equal to delta. This is just saying that asymptotically, at least if n is sufficiently large, the amount of error that we should expect to get is of order epsilon. And I should say this constant factor 2 can actually be improved to any 1 plus c for any c greater than 0, which is actually the optimal constant. In fact, this entire expression is minimax optimal, in the sense that, as we'll see next lecture, no estimator, if you're only given epsilon corrupted samples from a Gaussian, can ever do better than order epsilon error with high probability or an expectation. So it turns out actually for this problem, the median is optimal. Okay, so let's prove this. And to do so, I will prove, first of all, this following claim, which I claim is already sort of the moral reason why you should expect the median to be a good robust estimator for the mean of a Gaussian. Okay, what is it? The claim is the following. For any p, let q sub p be the pth quantile of the good points, so the good original uncorrupted points from a Gaussian. Then the claim is that the median of my corrupt set of points lies within the interval between the 1/2 minus epsilon quantile of my original set of points and the 1/2 plus epsilon quantile of my original set of points. Let's see pictorially why this must be the case. So imagine this is my set of points, S sub good. This is the original set of points, the IID samples from a Gaussian. And I have an adversary here who doesn't like me, who's very powerful, who gets to change an epsilon fraction of the points in any way he desires. He wants to mess up my median. He wants to move it to the right, let's say, as much as possible. So he wants to move it this direction as much as he can. Well, what is the adversary to do? Well, the only thing I argue he can really ever hope to do, the most that the median can be perturbed in this direction, is just by removing some points to the left here. Oops, excuse me. And adding back in the same number of points on the right. Right? But the constraint of the entire problem is that there's not that many outliers. The adversary can change at most an epsilon fraction of the points. But then when you think about it, this means that the new median can only ever be the 1/2 plus epsilon quantile of the original point set. And similarly, if they're trying to move the median to the left, then again, the smallest they can ever make it is the 1/2 minus epsilon quantile. Okay. And now, intuitively, we've already essentially removed the influence of the bad points. Okay, this is sort of the entire power of the median. Now all we care about is the 1/2 minus epsilon and 1/2 plus epsilon quantile of the original set of independent draws from a Gaussian. And I can already sketch essentially the rest of the proof. Because the point is that, again, S sub good is the set of independent draws from a Gaussian. And so the quantiles of S sub good should, at least when I have enough samples, begin to look like the 1/2 plus epsilon quantile of the population of the actual Gaussian. So just the 1 plus epsilon quantile of the Gaussian. And the 1/2 minus epsilon quantile similarly should behave like the 1/2 minus epsilon quantile of the Gaussian. But the Gaussian is smooth. And moreover, the mean of a Gaussian is also the median of the Gaussian, which is the 1/2 quantile of the Gaussian. And so, in particular, this should contain, this interval here, should contain the median and therefore also contain the mean. And moreover, because the Gaussian is smooth around 1/2, then this interval should be pretty small. And that's pretty much it. So let's make this rigorous now. What we're going to show is one direction of this, and then the other direction should follow symmetrically, so we'll omit it. So what we will show is the following. That the probability that the 1/2 minus epsilon quantile is less than mu minus t is less than this exp of minus 2n phi of t minus 1/2 minus epsilon squared. Sorry, the probability that this happens is this quantity, this exp of minus 2n phi of t minus 1/2 minus epsilon squared. And similarly, by exactly the same logic, but symmetric, you can also obtain that the probability that the upper quantile exceeds this is the same thing. And by the claim and a union bound over these two events, the theorem should follow directly. So we will only prove this bound, but the proofs of these two bounds are the same. Okay, so how do we reason about the 1/2 minus epsilon quantile? Well, the only thing we can really say is the following. That this event, that the 1/2 minus epsilon quantile is smaller than mu minus t, this happens if and only if the number of points in my set of good points, which are less than mu minus t, must exceed 1/2 minus epsilon times n. And let's see why this is true. Pictorially, what's going on is the following. So here is my 1/2 minus epsilon quantile, and here is my point mu minus t, which is supposed to be greater than this quantile. Well, the very definition of this quantile is that in this interval here, there are 1/2 minus epsilon times n points, which certainly means that there are also at least 1/2 minus epsilon n points to the left of mu minus t. Right? So now we just need to bound the probability of this event. And to do so, I'm just going to introduce a little bit of notation. So first of all, I'm going to call the points in S of good x sub 1 through x sub n. And recall that since these are the set of uncorrupted points, the original points, that by assumption, these are just independent draws from a Gaussian with mean mu and variance 1. And these are the great points. Now for each I, I'm going to define the following auxiliary variable, which is an indicator that xi minus mu is less than minus t. Okay, so it's 1 if this happens and 0 otherwise. So notice that since the xi's are independent Gaussians, the yi's are also independent, and they're Bernoulli random variables. Moreover, notice that the sum of the yi's, well, each xi which is less than mu minus t contributes 1 to the sum of the yi's. So that means the sum of the yi's is just this thing that we cared about, this quantity here. Okay, so to control this event that we originally cared about, it is equivalent to control the probability that some yi, that some yi exceeds 1/2 minus epsilon times n. Okay, so now let's do some quick calculations to understand these yi's. So first of all, as I said, the yi's are independent Bernoullis. And moreover, expectation of yi, well, this is simply the probability when xi is drawn from a Gaussian with mean mu and variance 1, the xi minus mu is less than minus t. But if x is a draw from a Gaussian with mean mu and variance 1, then of course xi minus mu is just a standard normal Gaussian. And so this is simply the event that, or the probability that a standard normal Gaussian is less than minus t, which is simply the CDF of a standard normal Gaussian at minus t. Okay? Great, so now we have a sum of these yi's, and we want to control the probability that they are greater than some event. So this is where tail bounds come into play. Right, so let me slightly rewrite this event. So this event is equivalent to the event that probability, or this probability here, is just equivalent to the probability that the average of the yi's exceeds 1/2 minus epsilon. I can slightly rewrite this by adding and subtracting phi of minus t. This is just the same as the probability, the average of the yi's, excuse me, exceeds phi of minus t plus 1/2 minus phi of minus t minus epsilon. Okay, so all I've done here is I've added and subtracted phi of minus t. Okay, and the reason why I do this is because this is the expectation of the average. And now we can apply something like Hufting's inequality. So recall Hufting's inequality says that for all r greater than 0, the probability that 1 over n sum yi exceeds its expectation, which is phi of minus t plus r, is something like exp of 2 times n times r squared. Okay, so we want to apply this to this being r, of course. But we first need to check that it satisfies the assumptions of Hufting's, namely that r is greater than 0. And indeed this is true, because you can rewrite this r. So we call this r as 1/2 minus phi of minus t minus epsilon. Well, I'm just going to use the fact that phi of minus t is equal to 1 minus phi of t by the symmetry of the Gaussian, to say that this is equal to 1/2 minus 1 minus phi of t minus epsilon, which I can rewrite as phi of t minus 1/2 plus epsilon. And we want this to be greater than or equal to 0, but of course this is just equivalent to the fact that t is greater than or equal to phi inverse of 1/2 plus epsilon, which is the assumption that we made on t. Great, so we are in the regime where Hufting's holds. And now the result just follows from applying Hufting's, because now this says that Hufting's implies that the probability that 1 over n sum yi exceeds this amount, 1/2 minus epsilon. This is at most exp of minus 2n times r. And r, as I rewrote briefly, is just phi t minus 1/2 plus epsilon. Which is equivalent to the expression that I had initially. So this completes the proof. Okay, so again, there's some calculations involved here near the end, but morally speaking, the only thing that's supposed to have happened is really, it happened initially all the way back here. Just this claim, which allowed us to say that instead of reasoning about the median of this corrupted set, it just suffices to reason about the slightly different quantiles of the original uncorrupted data set. Okay, so that's why, at a high level, this works. Okay, cool. So now let's turn our attention to the truncated mean, and recall that I was going to analyze the truncated mean in the setting where I assume my distribution just has bounded variance, so nothing else. Before I actually analyze the truncated mean, though, I first need to define what it means, and it takes a little bit more work to define it here than it did for the median. So what I'm going to take to be my truncated mean, which I hope you agree is a very reasonable notion, is the following. I'm going to define this notion of a truncated set. So for any epsilon greater than 0, and for any finite set of points, let trunc of epsilon of S, denoted this way, be the subset of S where I've removed the top epsilon quantile of points and the bottom epsilon quantile of points from S. Okay, and then I'm just going to let the truncated mean sub epsilon of S just be the mean of this remaining set of points. Okay, so pictorially it's a very simple operation. I have my set of points, I sort it, or I find its 1 plus epsilonth quantile and its epsilonth quantile. And then I just remove those points and take the mean. So I remove these points here, and then I take the mean of the remainder. Okay, so that's what my algorithm is going to be. And this is certainly a reasonable truncated mean. It certainly gets rid of this issue where a single point could be arbitrarily far away. And we will show that it works. So here's the theorem. So suppose S is an epsilon corrupted set of points from a distribution D that has mean mu and variance 1. And I need to make a couple of additional assumptions. So I need to assume that epsilon is at most 1/4 as opposed to 1/2 from before. And I want that n is sufficiently large. Then I have the following guarantee. If I take the truncated mean, where I truncate the top and bottom 2 epsilon quantiles, quantiles of S. The difference between that and the true mean is up to constants, at most root epsilon plus root 1 over n with high probability. Okay, let me make a couple of notes about this. So first of all, most of these constants are relatively arbitrary. So this 9 over 10th, for instance, is arbitrary. It can be replaced with any constant sufficiently close to 1 by suitably adjusting constants. Second, this epsilon less than 1/4 is less arbitrary in the sense that it is optimal for this algorithm. It's not too hard to see because since I'm removing the top 2 epsilon and bottom 2 epsilon quantiles, if epsilon exceeds 1/4, I will remove all the points. But for this this problem, it turns out you can actually get a better epsilon dependence here. So you can get a better breakdown point, but the breakdown point of this estimator is 1/4. Okay. And finally, I want to compare this with the guarantee that we got for the Gaussian setting. So if you recall, for the Gaussian setting, the error that we got, at least for epsilon sufficiently small, was of order epsilon, right? However, here, notice that our error is order root epsilon, even when n is sufficiently large. And this is sort of inherent. As we'll see in the next lecture, if all we're going to do is assume that a distribution has bounded variance, you can't do any better than this. Okay, so this is the trade-off that you pay for trying to be more general. So if you make stronger assumptions, you'll get a better result. But of course, it applies to less settings. And we'll talk about this a little bit more afterwards. Okay. So let's prove this. And to prove this, I will use the following main technical tools. And that's pretty much all I'll need. Okay, so the first is Chebyshev's inequality, which is a very standard tail-bound for distributions with bounded variance. And the second thing is another fairly standard calculation for distributions with bounded variance. It says that if I condition on any event E, and I take the expected mean, or difference from the mean, after hitting it with the indicator that x is in E, this quantity is at most the square root of the probability of my event E. Okay, and this is again another fairly straightforward calculation. It follows directly from Cauchy-Schwarz, for instance. So I will omit both of the proofs of this. Okay, so now what I'm going to do is the following. I want to argue about the set of points after truncation, and again there is a key claim here that will essentially give us everything that we want. And the claim is as follows. Let E be the following interval. It is the interval of radius root 2 over root epsilon around the true mean. Okay? So then with probability, let's say at least 99 over 100, all points, or I can just say the following, T is contained in E. So all the points that survive the truncation will lie within this critical interval E. Okay, let's see why this is true. So first, let's bound the probability that a good point lands outside of this interval. So if I'm actually drawn from D, the probability that I'm not within E, well, this is simply the probability that x minus mu exceeds root 2 over root epsilon, which by Chebyshev's is at most epsilon over 2. This is just by Chebyshev's. Okay? So now that means of my set of points that are originally good, the set of good points, I expect, roughly speaking, an epsilon over 2 times n number of them to land outside of this interval. And by a similar concentration argument to what we did in the Gaussian case, it's not too hard to see that at least if n is like at least 100 or so, we're not going to exceed this, the number of points that land outside of this interval from the good set won't exceed this count by more than double. So let me just write this. So with probability, let's say at least 99 over 100, we will have the number of points in S good such that X is not in E is at most epsilon n. Right, and again the idea is the following. I'm just going to, so again, let X or S good be X1 through Xn. I'm going to let Yi be the indicator that X is not in E. And again, these Yi's are independent Bernoullis. I can calculate their expectation. Their expectation is epsilon over 2. And I want to bound the event that the sum of the Yi's exceeds epsilon times n. And this is still going to be very unlikely because it's a sum of independent Bernoullis. So I'll leave that as an exercise, but it's not too hard to check. But this is sort of the key. And I'll condition on this event for the rest of this proof. So call this dagger. So condition on dagger. This implies that the largest, or I should say, well, this is exactly what it implies about the good points. But let me draw this pictorially, actually, sorry. What it means is that if I have this interval, so this is my interval, so this is mu minus root 2 over root epsilon. This is mu plus root 2 over root epsilon. So it says that here, this interval here, there's at most epsilon n points from S sub good. Okay, good. So now I claim that this actually gives us the claim directly. So let's see why. So let the points, let me clean this up slightly. So let these be the points in S. Okay, and let's say that my truncation threshold, or like the largest point that survived, or smallest point, let's say, that survived the truncation, landed outside of this interval. Let's say it landed here. Well, how could that happen? Recall that we throw out the bottom 2 epsilon quantile of my points in S. So that means there must have been 2 epsilon m points smaller than this in my set S. But where could these points have been? We know that there's at most epsilon n points outside of this entire interval. Like, there's at most epsilon n points here from the good points, and the total number of bad points is at most epsilon n. So that means there's no way that we could have thrown out 2 epsilon n points to the left of here. So that means that the largest point that survives the truncation must be inside. And similarly, the smallest, sorry, I guess I got that mixed up. The smallest point must be inside, and the largest point on this end must also be inside this interval. And that's what we wanted to show. Okay, so this is sort of the critical claim. This says that everything lies within this relatively small interval around the mean. But to finish up, we need to do a little bit more because now we could have thrown out some bad or good points as in addition to some bad points. And so we need to say that throwing out this small fraction of good points can't have changed my estimate by too much. Right? And to do this, let's do the following. Okay, so now let's compute the following. Observe. Expectation. The following expectation deviation is true. So I take the expectation of X, condition on the event that it lands within E, and I compare that to the true mean of the original distribution. I'm going to claim that this is small. This is small because of the following. This is simply expectation of X minus mu. Condition on E, I can just pull that in, certainly. And this is by the definition of conditioning. This is simply 1 over probability of E times expectation of X minus mu, condition on X in E. But it's not too hard to see that this is actually also the same as the 1 over probability of E times expectation of X minus mu times the indicator of the opposite event. Okay, just because these two things must sum up to 0. And now we're almost done because this quantity, 1 over probability of E, we know it's very large. It's certainly at least some constant. So this is like theta of 1. And this we know is small by our lemma, because the probability that I land outside of E is at most epsilon over 2. So this is up to constants, I'll say, at most root epsilon. So overall, this entire thing is up to constants at most root epsilon. Okay, and let me do one further calculation. I'm just going to kind of skip a lot of the details here, but I'm also going to argue that the sort of this variance, essentially, of x conditioned, again, on the event that I land with an E, by almost exactly the same argument here, is also at most up to constants 1. And this shouldn't be surprising. If I condition on the event that I land within a small interval around the mean, my variance shouldn't go up. Okay, so why have I done these things? Well, the point of these two calculations is that the random variable, this implies the random variable, which is, let me call it z, which is just x conditional on the event that it lands within this critical interval. This has bounded second moments, or bounded variance. So that's what this implies. Let me call this star star. And the mean of z is close to mu. So that's what this implies. Let's call it star star star. And moreover, I have a bunch of independent samples from this, because if I let S sub g consider the points in the good set that lie within this interval, each sample from that is an independent sample from this distribution of z. Okay, so let me just say this more precisely. The points in S sub g intersect E are IID distributed as z. Okay, and then therefore by a simple application of Chebyshev's inequality, I obtain that the average of the points within this set, so the empirical mean of x minus mu, this is at most up to constants root epsilon plus root 1 over n. Okay, this root epsilon comes from the fact that I'm actually not converging to mu, I'm converging to the mean of z, but we know from star 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 that the mean of z is not that far from mu. It's off by most root epsilon, and this root 1 over n is just the concentration of things with bounded second moment due to Chebyshev's. So this holds with high probability. At least let's say 99 over 100. And now we're almost done. So recall again, the whole goal is to compute the error of the truncated mean. And we can decompose the set of truncated points into the contribution from the good points and the contribution from the bad points. So we can write it as t intersect s good. And since we know that t is a subset of E, I might as well throw in this here. And similarly, I can throw in this here. Okay, so, oh, sorry, this is bad points. So this is fairly standard. And now let me just bound the error from these two terms. So I'm just going to say that the sum over x in this first thing of x minus mu, well, what is this? Well, what I can do is I can split this sum up. Actually, I can add back in the points that I improperly truncated from the good set. So I can say this is at least the following: t sg intersect E of x minus mu plus some error because of the points I threw out. X in t complement intersect s good intersect E of x minus mu. This we know is small from this bound. This is exactly what this is saying. So we know that this is at most up to constants. S could intersect E times root epsilon plus root 1 over n, which is certainly at most n times root epsilon plus root 1 over n. And at the same time, I claim that this has to be pretty small as well. And to see this is just because each individual point here is within this interval E. So each individual point can contribute at most up to some constant factor, root 1 over epsilon. And the number of points in total is at most epsilon times n. Just because the total number of points that I threw out is at most something like 4 times epsilon n. So overall, this is at most root epsilon times n. And similarly, the contribution from the bad points of x minus mu is, again, each individual point, because it lies within E, is at most root 1 over epsilon, and there's at most epsilon n points, because there's at most epsilon n points in the bad set. So overall, I guess this is again up to constants. This is at most root epsilon times n. So putting it all together, overall the total difference between the sum and mu is something like root epsilon we have sum x in S, or I should say t, of x minus mu is at most root epsilon plus root 1 over n times n. And when you divide through by n, that's exactly the result that we wanted originally. Okay, so a couple of quick comments before we finish up. So first of all, this argument also works under stronger assumptions. So for instance, if I make more assumptions about my distribution, so for instance, it has bounded kth moments. So if D has, if you just track where we used the properties of bounded second moment, that's essentially this Chebyshev, this fact that we had. What you get is an error guarantee that looks like epsilon to the 1 minus 1 over k plus root 1 over n. Okay, and this actually nicely sort of, you can see, interpolates between the bounded second moment case and the Gaussian case, because as k goes to infinity, this at least looks like it goes to epsilon. However, there is a key difference here. In particular, if D is Gaussian, in fact, we don't quite recover the guarantees of the median. What we get is something like the following. Root log 1 over epsilon plus root 1 over n. And this is actually inherent for this algorithm, and it's inherent for actually a good reason. And the reason is because the Gaussian actually requires, or sorry, the median estimator, when you think about it, uses a lot of properties of the Gaussian. So it uses stuff like that the median is close to the mean. It uses the fact that around the mean, the CDF is smooth, and all these things in addition to the fact that the Gaussian nicely concentrates. But here, this estimator, all it's going to ever use in the analysis is that the Gaussian concentrates. So this applies for more generally beyond Gaussian to things which have sub-Gaussian tails. And the median does not, at least necessarily. So here you can actually see a trade-off. You can actually get a better guarantee. You can get epsilon rather than epsilon root log 1 over epsilon. But there's a trade-off here in terms of it actually needs to be exactly Gaussian, or it needs to have at least more structure than the truncated mean needs. And this is kind of a philosophical question because there's a trade-off here. The goal is to design robust algorithms, so it's not clear how useful it is potentially if your algorithm is still brittle to your model that needs to be exactly Gaussian rather than sub-Gaussian. But at the same time, you do get better error guarantees. Okay, so that's pretty much all I have to say for now. So next lecture, we will go into statistical models of corruption as well as lower bounds. And we will demonstrate that essentially the bounds that we had here are optimal. Okay, see you.